Good afternoon. The topic of today's lecture would be thermodynamic potentials, as written here. So before we start, let's refresh a bit what happened during the previous lectures. So first of all, I have introduced previously laws of thermodynamics, and Zero's law led me to introduction of the concept of temperature. The first law allowed me to introduce internal energy, and the second law led to a new function which kind of describes irreversibility and is called entropy. And all of these are the functions of state. So if the state can be described by a number of variables, AI, and for those, for the ideal gas, that is, or for the gas, those are just simply the pressure and volume, then I can say that all of these functions for the gas are the functions of pressure and volume. Of course, if you consider other kind of substances, for example, magnetics, or if you study solids, then the number of variables would increase. But in the most simple case, all of these are the functions of pressure and volume. Okay, and also we have kind of combined the definition of the entropy. The thermodynamic definition of entropy is this, and it can be understood as the change in entropy in a reversible process equals to the amount of heat obtained by the system divided by the temperature of the system. And if I combine this definition with the first law of thermodynamics, then what I would get is the following, that TdS equals to du plus PdV, where PdV corresponds to the small amount of work done in this process. So that is it. In a compressed form, this is an extract of everything that which we have done during our two previous lectures. And actually, these three are the only functions of the state that we can introduce thermodynamically or based on thermodynamic laws. And any other function of state, let's say, for example, that we have invented some other function of state, and let's call it y, the function of state y can be presented as some sort of function of the previous functions of state, and also the variables which describe the state themselves. But so it means that actually, based on the state, I can introduce almost an infinite amount of functions as I wish. But some of those functions have some physical meaning. So those functions which are usually introduced in addition to those, and these functions are called thermodynamic potentials. Internal energy is one of those thermodynamic potentials. So that is some function u, and the differential of the thermodynamic potential is given as TdS minus PdV. I will explain further why do I write the differentials of the thermodynamic potentials, because all of this has some special meaning. So just by now, just simply write that down, and the explanation would follow. That's the first thermodynamic potential, internal energy. The second one is favored by chemists, and that is called enthalpy. And the definition of enthalpy is U plus PV. The differential of this function is du plus pdv plus vdp. And after I plug in this expression for du here, I would get TdS plus vdp. So let's look at the differences between these two functions. Let's look at the physical meaning of them. For example, if I consider the internal energy, then change in the internal energy at the constant volume would be exactly equal to the amount of heat supplied to the system at the constant volume. So you can consider it as one of the physical explanations or meanings of this internal energy function. But if I consider this function h, then actually one would see that the increment in the enthalpy is actually exactly equal to the amount of heat supplied to the system at the constant pressure. So the change in internal energy is the amount of heat supplied at constant volume. The change in enthalpy is the amount of heat supplied at constant pressure. Okay, that's not the only one. The third one is called PreEnergy. Well, it actually has lots of different names. One of them PreEnergy. The other one is Helmholtz PreEnergy. Helmholtz PreEnergy. Or Helmholtz potential. Helmholtz potential. And also, the definition of this is U minus Ts. And if you look at the differential of this, that would be du minus TdS minus S dt. Plugging in the differential of U, that would give us minus S dt minus PdV. And the final one also has lots of different names. One of them is free enthalpy. Also, Gibbs free energy or Gibbs potential. And here, Helmholtz and Gibbs are surnames of prominent scientists who have done lots of contributions to the field of thermodynamics. And this one is defined as G equals to U plus PV minus TS, or equivalently H minus TS, or equivalently F plus PV. So all of this are exact identities. And if I write the differential of this thermodynamic potential, then that would give me the following. And it would be, okay, let's start from this one. dF plus PdV plus VdP. So after I insert this kind of F here, that would give me minus S dt plus VdP. Okay, there should be also some kind of explanation when this one is considered free energy, because this has nothing to do with the cost of energy and it being free or not. So the meaning of this potential F is that the increment, or actually the decrement of this potential would be exactly equal to the work done by the system at constant temperature. So let's look at this further. So if I have a constant temperature, then my dF would be exactly equal to minus PdV, according to this one. I just assume that dt equals to 0. So that leaves me out with minus PdV. So that would mean that minus dF equals to PdV if I consider it at a constant temperature. And that is actually exactly the amount of work done by the system. But that is valid only for the reversible process. If I consider, for example, reversible process, then that would slightly change, and I would say that the amount of work done by the system at the constant temperature would be less or equal than the change of the free energy. So actually free energy represents you the ability of the system to do some work on the environment under the constant temperature. And moreover, so from the second law of thermodynamics, it follows that if the process is not completely reversible, then this is actually the limit of the work which can be done between two different states of the system. So that is the maximum work which can be done, maximum of work which can be done by the system. Well, free enthalpy also has some kind of a similar meaning. I'm not going to go into too much details, but free enthalpy is also pretty much favored by chemists because, well, first of all, if you consider a system at the constant pressure and constant temperature, then if you insert this into this, then you would obtain that dg equals to 0. dg equals to 0 at constant p and t. And that means that in the reversible process, this function is extremal. So it can be either the maximum or minimum, but well, we can consider that further. And it turns out that if some chemical reaction can happen in my system under the constant pressure and temperature, then when this chemical reaction goes on, then this chemical potential of this free enthalpy can only decrease. So that can be less or equal. But in here, okay, these G0 and G of P and T are not exactly the functions of the pressure and temperature, so we need to have an additional degree of freedom of the system. For example, if I have chemical reaction in my system, that means that, okay, there are some transformations going on, and there exists an additional degree of freedom which describes, for example, the amount of the products of reaction. So that means that these values would change in such a way that overall Gibbs potential would decrease. And in the final state, this Gibbs energy would reach the minimum. Okay, so that goes for this free enthalpy function. Okay. So now that I have introduced all of these functions, I need to explain why I'm so much caring about these differentials, so that I have written all of them for all of these functions. If you look at these differentials, they kind of look like as a differential for the function of multiple variables. So let's write it. For example, I have some arbitrary function of two variables a and b. Then this differential can be written as df over dA. So this is partial derivative of the function f over a multiplied by dA plus this. So that implies that I can consider these functions as a function of these two variables. And, okay, the variables you see in these differentials are called canonic variables. So let's see the main difference from the variables which I have discussed before. For example, I have said that if you have internal energy as a function of, for example, volume and temperature, then this is called caloric equation of state. As you see, it's pretty much different from having an internal energy as a function of entropy and volume. When you have your internal energy as a function of entropy and volume, then this is called not a caloric, but canonic equation of state. And the feature of this equation, the main feature of this equation, that one caloric equation of state replaces two equations of state for the matter. So canonic equation of state replaces both thermic and caloric equations of state. So I have said previously that for any substance you may have two equations of state, but when you have a canonic equation of state, you can have only one equation which is sufficient to replace the previous two. And now I'm going to prove this for this particular equation for u as a function of S and V. So how can we go around with this kind of an equation of state? Well, I can prove that this equation of state can replace both of these if I am able to derive thermic and caloric equation of state from the canonic equation of state. So that would conclude my proof of this equivalence. Okay, let's show it. As I have said previously, the differential is TdS minus PdV. And from this, it follows that actually this kind of a temperature can be determined as a partial derivative of internal energy over the entropy at a constant volume, while the pressure or minus pressure is partial derivative of internal energy over the volume at a constant entropy. Okay, or I can write that pressure is minus du over dV at the constant entropy. So this one step allows you to determine temperature as a function of, again, entropy and volume, and pressure as a function of entropy and volume. When you have these two equations, you can consider this as a set of equations. And for example, from this one, you can try to express entropy as a function of temperature and volume, and then insert it here. And what you get after this insertion is that you obtain, as a result, pressure as a function of volume and temperature. So these are actually the steps which allow you to find out thermic equation of state, because thermic equation of state is the equation which bundles together pressure, volume, and temperature into a single function. Similarly, you can determine, after that, you can easily determine the caloric equation of state. To do this, you can start from this step where you have entropy as a function of volume and temperature and plug it into the initial canonic equation of state. After this, you would have internal energy as a function of temperature and volume. So that would give you caloric equation of state. So that concludes my proof that canonic equation of state is capable of replacing two equations of state. So instead of considering two equations, you can consider only one of them. And moreover, I'm not going to prove each of those statements, but actually any kind of thermodynamic potential presented as a function of its own canonic variables, PreEnergy as a function of temperature and volume, PreEnthalpy as a function of temperature and pressure, would give you would give you a canonic equation of state. And from that canonic equation of state, you can obtain, again, caloric and thermic equations of state. Okay, I have a question from online viewers. It says, does thermodynamic potential has an explicit definition itself? Well, I'm kind of unable to understand, but I can say that there is a reason why all of these functions, why these four particular functions of state are called thermodynamic potentials. And the main reason is due to these properties, which I have written here. It says that I want to determine some quantity, and this quantity can be determined as the difference between the thermodynamic potential in the initial and final state. This pretty much works like potential energy or some electrostatic or gravitational potential in mechanics, in which you can determine, for example, the work of force done by the gravity force by the change of potential energy in the gravitation field. So this pretty much looks quite the same. So in here you can determine the functions, like for example the heat supply to the system, which are generally some functions which are related to the process which connects the initial and final point, by calculating the difference or the increment or the decrement of some function which depends on the initial and the final state. So that's why these four functions are considered or often called thermodynamic potentials. But I see no more like sensible explanation to this. So you can say that this can be attributed to the history in which, or to this kind of a similarity between mechanics and thermodynamics, for which reason they were called thermodynamic potentials. In the same way with these names like PreEnergy. So again, as I said, nothing to do with the cost of energy, but something to do with the work which can be done by the system at the constant temperature. And also this PreEnthalpy, which has somewhat more complicated meaning. Well, I'm not going to go into too much details. You can say that also that this PreEnthalpy can be considered as the maximum amount of so-called useful work which can be done by the system at the constant temperature. So by useful work, I mean that in this way, in here, when I consider the processes, that I have my system, in contact with some reservoir at a constant temperature T, and the work done by the system can be divided into two classes: the work done on this environment and the work done on some kind of external bodies. And in here, useful work would be the work done on the external bodies. So I discard this amount of work which is done on this reservoir by itself. So in here, it includes the work done on the reservoir. But when I calculate the change of free enthalpy, then that would give me, for example, this kind of a useful work. Again, so that is kind of explains why all of these, why they have all of these weird names, because these are just simply some functions, functions of state. So I just have other functions of state and somehow modify them and obtain a new function of state. As I have said at the start of the lecture, you can do this in infinite amount, number of ways. So, but these three particular ways are, well, they are considered meaningful, okay, or more meaningful than other ways. Okay, so let's go to the applications of the thermodynamic potentials, because since you have something being the function of state, actually it leads to some consequences, and I can get some kind of a properties of these materials based only on the fact that these internal energy, enthalpy, free energy, and free enthalpy are just functions of state. So let me discuss it in more detail. Okay, let's start with the free energy, because what follows from the equation for free energy is typically used the most. So for the free energy, we know that dF is minus S dt minus pdV. And as I have already done previously, you can consider this and this as partial derivatives of this function f over temperature and volume. So I can write that minus s is equal to the partial derivative of the function f over temperature at the constant volume, while minus p is the partial derivative of f over the volume and at a constant temperature. And from this, I can obtain something which doesn't even require the knowledge of the function f itself. As you know from calculus, that if you have, for example, good enough function of two variables, then for this function, the mixed derivatives of such type, df over dA dB, should be equal to the mixed derivative over dB dA. Have you studied this one? Not yet. But that is actually valid. So, well, actually it can be violated, but the function should be bad enough to do this. But if we work in physics, typically all the functions in physics are good. So that means that in a mathematical sense they are good. So they have derivatives. They have not only the derivatives, but those derivatives are continuous functions themselves. So good functions. And they can have even multiple derivatives over all of these variables. And for these good functions, this is valid. So you can take the partial derivative in any way you want, and then you obtain the same result. Let me show one example to explain this. Since you haven't studied this in calculus, then I need to give some kind of a proper example. Let's say we have a function of the type, like for example, a squared plus a times e to the power of b. So this is a function of two variables. So let's calculate explicitly these mixed variables, mixed derivatives. So the mixed derivative, okay, first the partial derivative df over dA gives you 2a plus e to the b, while the derivative of f over b gives you a e to the b. So now I have these two. Now let's calculate the mixed derivative. Oops, I should have these two here. So the second derivative, df over dA dB. So that means that first I have calculated the partial derivative over a, and then I find the partial derivative of this over b. So that means that the first term is a constant with respect to b, so I can discard that. And what's meaningful here is this e to the b, and the derivative of e to the b with respect to b would give me again e to the b. And now let's calculate the mixed derivative for this one, and that would give me second derivative over dB dA. And as I look at this, as a function of a, it's just a linear function. So the derivative of this with respect to a is just the coefficient, and that is e to the b again. So as you see, whatever the order of finding these derivatives, the final result remains the same. That's e to the b. So this is the main statement here. So it doesn't matter in the mixed derivative in which order you actually take those partial derivatives of your good enough function. Of course, in calculus, you would be given a counterexample to that, but that would be quite bad function. Okay. So now I'm going to apply the same to this equation, to this one, and first I can find that second derivative of f over temperature and volume should be equal to the second derivative of f over volume and temperature. So okay, over temperature that gives me minus s, and now I take the derivative of this over volume, so that would give me minus ds over dv at the constant temperature. And that would be equal minus dp over dt at the constant volume. Of course, I have minus and minus on the left-hand side and right-hand side, so I can abandon these minuses, and that would give me this kind of expression. Okay, what is so interesting about these expressions? Okay, this one is something which is related to thermic equation of state, because it involves only pressure, volume, and temperature. So this can be determined from thermic equation of state. While this one about the entropy change at the constant volume is actually pretty much related to the caloric equation of state, because you need to understand, to know the caloric equation of state in order to describe temperature, or entropy. Entropy is related to the amounts of heat given to the system in a reversible process. So that involves, if you consider amounts of heat, that involves the internal energy and work done by the system. And if you know, you need to know the internal energy as a function of volume and temperature in order to obtain entropy. So this is something which is related to the caloric equation of state. So by means of this equation, I can establish some connection between caloric and thermic equations of state. So this is what is actually good about this. Let's continue further. and find out exactly what kind of a connection between two equations of state is established by this one. So as I said that, okay, du equals to T ds minus P dV. So if you want to find to find the entropy, you should know internal energy. So for this we know that ds over dV at constant temperature is equal to dP over dt at constant volume. So that means that actually, in order to use this expression, I need to consider some process at a constant temperature. So du at the constant temperature would be equal to T ds at constant temperature minus P dV. Then that would be something like T, then goes ds over dV at constant temperature times dV minus P dV. So that would give me T ds over dV at the constant temperature minus pressure times dV. And all of that again at a constant temperature. Then if I divide du by dV at the constant temperature, that would give me the partial derivative du over dV at the constant temperature, and that would be T times ds by dV. Okay, then using this, I get that this is actually T times dP over dt at the constant volume minus pressure. So that is exactly the relationship between the caloric equation of state and thermic equation of state, because the right-hand side depends only on the thermic equation of state, while the left-hand side has something to do with caloric equation of state, U as a function of volume and temperature. And we can partly guess the internal energy as a function of volume and temperature. We cannot describe anything about, we cannot understand anything about the dependence of internal energy on the temperature, but we can guess the dependence of internal energy on the volume. Okay, let's put, for example, the equation of state for the ideal gas. For 1 mole of ideal gas, PV equals to RT. So I can write that, okay, pressure is RT over V. So dP over dt at the constant volume would be R over V. Okay, after I insert it into here, then I get that for the ideal gas, du over dV at the constant temperature is RT over V minus P, and that is 0, because RT over V is the pressure, and pressure minus pressure is 0. So it says that if you have the ideal gas, whose equation of state is this, then the internal energy of the ideal gas would be independent of volume. But this one is actually valid for any kind of substance. It doesn't need to be the ideal gas. I have used the ideal gas to show you how this works. So it says that actually the independence of internal energy of the ideal gas of the volume can be inferred from thermic equation of state. And this one expression is what enabled us to do such kind of a conclusion. So I can go further and derive similar equations for all of the 4 thermodynamic functions. And these sort of equations are called Maxwell's relations. Okay, I'm going to give the derivation of another one of them, which comes from Gibbs Energy, because it's the second most used Maxwell's relation in addition to this one. So I need to use the following, that dg equals to minus s dt plus v dp. So I am again following the same procedure, that dg over dt is minus s dg over dp, okay, at a constant temperature, here goes at constant pressure, is volume. Then I calculate mixed derivatives. That would be minus ds over dp at the constant temperature. And here goes again the second derivative of the pressure and temperature, which is dv over dt at the constant pressure. And again, you see some kind of a connection between these two, because this one is somewhat related to caloric equation of state, while this one is related to thermic equation of state. So I can write that dv over dt at the constant pressure equals to minus ds over dp at a constant temperature. Okay. Okay. Now I need somehow to explain what all of these Maxwell's relations mean. And probably by now you would not kind of understand my explanation, but nevertheless I would give it. And after you study the relevant topics in calculus, you need to come back to all of this and see if you understand these expressions better. In order to give this explanation, I'm going to introduce a new concept. This concept is a generalization of the derivative. So let's say you have some y as a function of x. Then you can calculate the derivative of this function, dy over dx, like this. And I can easily explain the main meaning of this derivative. So if I plot the function given by this, for example, that is the line which represents exactly this function, then the main meaning of the derivative is the ratio between this small displacement here and change in the function here. So if the derivative is large, that means that small change in the variable produces the great change in the function itself. Or you can consider it in other way. So you can consider this as a coordinate change. So let's say I have these two axes aligned parallel with each other, and I have some points on x-axis being transformed in another points on y-axis. Now, what actually derivative means? The derivative means that a small interval on the x-axis has its length multiplied by the derivative function on y-axis. Okay, so what I establish is the relationship between length of a short interval and the corresponding length of the short interval on y-axis, when x and y have the dependence on each other. So I can I can convert each x-axis pointed and at each point on x-axis into another point on y-axis. So now I'm going to generalize the concept of derivative and to go into multiple dimensions. That would give me, instead of the derivative, the thing which is called Jacobian. So now let's say that I have multiple functions. Well, let's say I have or x and y as independent variables, and I transform a pair of on two-dimensional plane, a point on a two-dimensional plane, into another point on a two-dimensional plane. Let's say Mn. So I have some kind of a transformation, let's say, which determines me this change. So in here I have, okay, y, x. So any point on xy plane is transformed into the point on Mn plane. Okay. So this transformation can be given by two functions, m as a function of x and y, and n as a function of x and y. So now what I want to understand is, let's say I choose a small rectangle here, which has the width of dx and the height of dy, and I want to find out how this small rectangle is being transformed by these functions. And okay, so since this rectangle, let's say that this rectangle includes some point x0 and y0, and near this point x0 and y0, I can represent these functions as linear functions. So I can say that actually m equals to m of x0, y0, plus partial derivative of f over x times x minus x0 plus partial derivative of f over y times y minus y0. And the same happens to this function n. This procedure is called linearization. So I change my functions into linear functions which are approximately equal to the initial functions in a small interval near this point x0, y0. Okay, dm, here goes dm, and here goes dn over dx times x minus x0 plus dn over dy times y minus y0. So now it looks like somewhat kind of a difficult algebraic stuff, but the main meaning of this algebraic stuff is that the rectangle here is being transformed into parallelogram here. Oops. And now I'm going to do this without the derivation, but if I consider the ratio of areas of this parallelogram and the initial rectangle, so let's say dA in variables mn over the dA in variables xy. So this one is actually equal to dx dy. Then this ratio would be equal to the Jacobian G, which is the determinant of the following matrix, which is dm over dx, dn over dx, and here goes dm over dy, and dn over dy. So if you calculate the determinant, you would get the ratio between these areas. But, and you should, well, there is another stuff in here. The determinant can be negative. The determinant can be negative, and that would actually mean, like, for example, if my dx is negative, then in here, this area would become positive. So that depends actually on the directions of these changes. So if I have let's say positive changes in x and y, and that would transform into these kinds of vectors in here, then this is positive. But if I have, for example, the following vectors corresponding to my dx and dy, like for example, one goes here, another one goes here, then this area of this parallelogram is considered negative. So this is related to the orientation of that area. And now, finally, after all of this, I give you the meaning, the physical or mathematical meaning of these Maxwell's relations. And that's the following: that any closed area on the PV diagram should be exactly equal to the area on TS diagram. So of course I can do the transformation. I know that my temperature is the function of state, that entropy is the function of state. So I have a one-to-one correspondence between my PV diagram and TS diagram. And it says that any kind of enclosed loop on PV diagram should have exactly the same area as the closed loop on the TS diagram. So that's the main meaning of those Maxwell's relations. And it can be written in the Jacobian form. It would say that, so the Jacobian actually has a, okay, it has a notation. The notation is pretty much almost the same as notation for the derivative. It writes like follows: d mn over d, let's say, xy. So that's how this Jacobian is formally written. So in between these two pairs of variables. So I can write that actually that d ts is over d pressure volume is 1. And from this expression I can actually obtain all of these Maxwell's relations. So let's, for example, go. Let's go for the expression for free energy, this one. ds over dv at constant temperature equals to dp over dt at constant volume. Let's obtain it from this expression. Okay, d ts over dpv is 1. So I can write that d ts over dtv over dpv over dtv is 1, or I can write that dts over dtv equals to dpv over dtv. And actually, when one of these variables coincides in both of these, then Jacobian is quite simple to understand. So let's write it. For example, dt over dt now goes, here goes ds over dt, here goes again dt over dv, and here goes ds over dv. Okay, this one is actually at a constant temperature. Here, this one is at a constant volume. This one at a constant volume. This one at a constant temperature. Okay, this one is 0. So this one is 1, dt over dt. So overall, this determinant is actually equal to ds over dv at a constant temperature. So what is left over, that I take my temperature here and get it inside here, so I take it as a constant value here, and here what remains is ds over dv. It can be very simply understood in terms of the original logic of transformations. So it says actually that when one of my variables is the same, so let's say I have ts, and here goes tv. So that means that for any point here, the temperature is preserved. Temperature is just temperature everywhere. But then actually you have also some changes, so some entropy transforms into some volume. So now, if I have a rectangle here, that means that what I have here is also a parallelepiped, or parallelogram, which has one of these axes, which has one of the sides aligned parallel to the axis, and this is dt and dt here, exactly the same, and what is left over is here. Oops. Wait a second. Here temperature is constant, so here again temperature is constant. So dt goes here actually. dt goes here, corresponds to the dt here, and here is ds over dv, actually dv over ds at the constant temperature times ds. So now this ratio between these two areas would be proportional to dv over ds at a constant temperature. Or I can actually invert it here and get ds over dv at the constant temperature. So that's what it means when one variable is coinciding. So that exactly refers back to the derivative. So instead of the ratio of areas, I again go to the areas of line. So the area of line is actually the length, so the measure of line. And actually this concept of Jacobian can be generalized to multiple dimensions, not only 2 dimensions, but n dimensions. So you can have, like, for example, the ratio between volumes, or 4-dimensional volumes, and so on and so forth. So you can say that Jacobian is a generalization of the derivative in this sense. Okay, so now it actually means that dTs over dTv is ds over dv at a constant temperature. And the right-hand side, I have the one variable which coincides. So the right-hand side is dp over dt at the constant volume. So that again gives me the expression which I had at the very beginning. So I believe that this kind of a crude but not understandable at this point, the proof that all of these Maxwell's relations are related to the fact that the same area is enclosed by the curve on the PV diagram and TS diagram. And you can easily understand that, because the area of the curve enclosed on the TS diagram is the amount of heat, total amount of heat obtained by the gas in this cycle, while the area enclosed on the PV diagram is the amount of work done by the gas in the process. And since in the cycle the initial and the final state of the gas are exactly the same, that means that according to the first law of thermodynamics, the amount of heat supplied to the gas equals to the change in internal energy, which is 0 in a cyclic process, and this equals to the amount of work done by the gas. So this represents the equality of the amount of heat given to the gas and the amount of work done by the gas in a cyclic process. On this board, I have briefly written all of the conclusions of the first part because it was so lengthy and so difficult, so I have decided to write main conclusions of what have happened in the first part. So I was able to introduce 4 main thermodynamic potentials using the well-known functions of state, which are temperature, entropy, and internal energy. Also, I have introduced the concept of the canonic equation of state. So that is if you have a thermodynamic potential written in canonic variables, then this equation allows you to replace both the caloric and thermic equations of state. So that gives you a full and complete description of thermodynamic properties of the system. So that allows you to determine everything, not only caloric and thermic equations of state. It allows you to determine heat capacities at any kind of, for example, at the constant volume, at the constant pressure, some compressibility coefficients, thermal expansion coefficients, whatever you can get out of this. And also the concept of Maxwell's relations, in which you take the thermodynamic potential in its canonic variables and then calculate mixed derivatives using different ordering of the derivatives. And that allows you to have 4 relations which are equivalent to the following fact, that any area enclosed by the loop on the PV diagram should be exactly equal to the area enclosed on TS diagram. So this is the main physical meaning of these relations. And by means of Maxwell's relations, you can determine the relations between the caloric and thermic equations of state. I have shown it determining, for example, the derivative of internal energy over the volume at a constant temperature, which I was able to express in terms only related to thermic equation of state. Okay. So basically, that means that for the full and complete description of thermodynamic system, it is enough to have thermic equation of state so the dependence of temperature on other parameters. Temperature is a function of pressure and volume, for example. And you also need caloric equation of state at some volume. So now goes some new material, so I just continue in this discussion. Since I was able to determine this derivative, that means that I don't need to know complete function u as a function of volume and temperature. It's enough for me to have this function only at some volume v0, because I can determine internal energy at any other volume as follows. So since I know this partial derivative, that means that I can calculate, so let's say this is temperature, this is volume. I know my function u as a function of volume and temperature at some volume v0. If I want to determine the internal energy at any other volume, I can integrate the derivative of internal energy over the volume and can integrate all the way from the volume v0 to the volume v. And that would allow me to obtain this function at any other volume. As far as I know this function at any fixed volume v0, then I can determine it everywhere. So that is actually the main meaning of that derivative, which I have determined previously. And well, there is some comment about this thermic equation of state here. The temperature in this thermic equation of state is not empiric temperature. This temperature is thermodynamic temperature. So T is thermodynamic temperature. So please remember the difference between thermodynamic and empiric temperature scales. Empiric temperature scale, you can determine temperature like any parameter, for example, length of the aluminum wire at different conditions. So that would give you an empiric temperature scale. And there are multiple ways to introduce empiric temperature scale, but there are much less number of ways to determine thermodynamic temperature scale, because thermodynamic temperature scale is related to Carnot theorem. And well, please check out the definition of thermodynamic temperature scale, which I have given during the previous lecture. Okay, now let's apply our knowledge to some other systems, but before that, we need also to learn another trick related to those partial derivatives. And the trick is follows, that if you have some function f of a, b, and c, some relationship between three variables a, b, and c, and for example, you are able to determine a as a function of b and c, and b as a function of a and c, or c as a function of a and b, then you can draw the following conclusion. For example, dA over dB at a constant c times dB over dC at a constant a times dC over dA at a constant b is -1. It almost looks like some kind of expression for the chain rule for the derivatives, but it looks slightly different, because if you consider chain rule for derivatives, so let's say you have function f as a function of g, and in turn g is some function of x, then you know that according to the chain rule, df over dx is equal to df over dg times dg over dx. All of this behaves as if these df, dg, and dx are some real quantities, and you can actually cancel out them if they appear in the numerator and denominator. But in here, I have the same quantities for the partial derivatives, and both of them they appear first in the numerator and then in the denominator, and here for dB and dC, but altogether that gives you -1. So that deserves some explanation. How it happened to be so. Okay. So let's say that I know the function a as a function of b and c. So then I can write that dA is equal to the derivative of a over b times dB plus dA over dC times dC. So that's the usual differential for the two-variable function. And of course, here goes dA over dB at the constant c. Here goes dA over dC at the constant b. And now if I want to determine dB over dC at the constant a, I need to take dA equal to 0. So then I can write that 0 equals to dA over dB at the constant c times dB at the constant a. dB at constant a, so I have an index a here, plus dA over dC at a constant b times dC at constant a. And from here I can get dB over dC at constant A. dB over dC at constant A is equal to dB at constant A over dC at constant A. And that would be, from this expression, that would be minus dA over dC at constant B over dA over dB at constant C. Okay, so now I take this to the left-hand side and get the next thing. So now I have that dB over dC at constant A times dA over dB at constant C equals to minus dA over dC at the constant B. That is almost this expression. What I need to finally do is that if I have C as a functions of A and B, then dC over dA at the constant B would be equal to 1 over dA over dC at the constant B. This is actually quite obvious, because if you fix, for example, the value of B, then to some change of dA corresponds some change of C. dA corresponds to some dC, and if you take, like, at the constant B, so if you take this one, dC over dA at constant B, that would give you dCB over dAB. But if you look at this one, this is actually the reciprocal thing, so that's why this can be easily established, and from this follows this identity. Well, so this is a general mathematical stuff. Now, if we want to apply it to thermodynamics, we need to consider something, some kind of an example in which that can be applied. So now let's consider the equation of state. Actually, the equation of state for the gas is exactly the same, works in the same way. Some function of pressure, volume, and temperature equals to 0. So if you have an ideal gas, so let's say for 1 mole of ideal gas, PV equals to RT, so you can write that the function PV minus RT, the function of pressure, volume, and temperature is identically equals to 0. So for any equation of state, you can write it in the same way, that there is some kind of a functional dependence between these three variables, from which you can get pressure as a function of volume and temperature, volume as a function of pressure and temperature as a function of pressure and volume. So now I can write that according to this identity, that dP over dV at the constant temperature times times dV over dt at a constant pressure times dt over dP at a constant volume is -1. So nothing has changed. But then I can introduce some few coefficients which are typically measured in experiments. Okay, one of them is volumetric coefficient of thermal expansion. Volumetric coefficient. Okay, now let's wait a bit before it dries up, and I can also volumetric coefficient of thermal expansion. Thermal expansion. We have some letter. Alpha. Alpha is 1 over the volume times dV over dt at the constant pressure. So why do I have 1 over the volume in the whole of this expression? The reason is that the more the initial volume of my gas is, the larger the increment of volume. So if I want for this expression to be valid to be independent of volume, then I need to divide it by volume. So if I have twice the amount of gas, then I would have twice the amount of volume and twice the amount of the increment of volume. So without this 1 over V, that would not do, because in here, this dV over dt at a constant pressure would be proportional to the amount of gas. But if I want to have some material quantity which is independent of the amount of my gas, then I need to divide over the volume. So this is the volumetric coefficient of thermal expansion. And it is measured in kelvins to the -1, because dimensions for volumes in here, they cancel out. Another interesting coefficient is isothermal compressibility. Isothermal compressibility. Compressibility. So this coefficient which determines the ability of matter to be compressed at the constant temperature. And beta T equals to -1 over V times dV over dP at a constant temperature. So the main question is, why do I have minus here? Because you might now understand why I have 1 over volume here, for exactly the same reason why I had it in the previous expression. But minus here is due to the fact that if I increase the pressure, the volume is decreasing. That's why this derivative is negative. And since the derivative is negative, it is much more convenient to have a positively valued function, so the compressibility is obtained by multiplying that by -1. So when I have greater compressibility, if I increase this beta T, that means that I can easily compress more and more easily. So my matter, or my gas, or liquid is more easily compressed with respect to the other matter which has lower this quantity. So that's compressibility. And the third one is thermal pressure coefficient. Thermal pressure coefficient. Which is given as 1 over P times dP over dt at a constant volume. Well, actually, there is no need to have it 1 over p here, but, well, I think this is a part of the traditional definition. So it says by how much percent your pressure increases when you increase the temperature at a constant volume. So if you have constant pressure, then the volume would increase due to the thermal expansion. But if you, let's say, do not allow your gas to expand, then it means that it would produce the increase in pressure. Okay, and from this expression it follows that actually okay, from this it follows that dV over dt at constant p is alpha v. dV over dP at the constant temperature is minus beta T times volume. And finally, dP over dt at constant volume is lambda p. Okay, now we try to construct this. So I have dP over dV at constant temperature. So this is actually this one inverted. So that would give me minus 1 over beta TV times dV over dt at the constant pressure times alpha V multiplied by dP over, dt over dP at constant volume. So that would be inverted lambda p. And that is minus 1. Okay, coincidentally, I have minus here, so minus by minus gives me plus. And at the end, volume is cancelled out. So I can write that alpha equals to beta T lambda P. So actually, of 3 of those coefficients, only 2 of them are independent. You can derive the third one out of 2 of them. And why these coefficients are given so much attention here is that they can be measured in the experiment. So you can conduct an experiment, and the direct outcome of that experiment would be one of those coefficients. And when you have 2 of them, then that allows you to determine the third one. And now let's give an example on how all of the thermodynamic stuff which I have introduced before can be used the system which is not the ideal gas. Okay, everything is quite simple as long as we deal with ideal gas, but thermodynamics is designed in such a way that you can explain just about anything, not only ideal gas, which is a very good example, but nothing more than that. So let's try to describe surfaces. So when you have 2 different substances, there is a surface which separates one substance from another. And one of the most simple examples is the surface between water and air. And there is surface in between them. And as you know, there is also some surface tension associated with that surface. So let's describe thermodynamics of such kinds of surfaces. The experiments show, for example, if you have some frame, and in this frame one of the parts can be moving, and you have, let's say, a water surface which is spanning over this area, and you try to move this thing over there. So you need to apply some force. Well, let's say like you have, for example, like area which is made out of that which is made out of soap. So when you have some soap and you put something into the soap, then you would have, well, if you have done some bubbles in a childhood, then you see how it works. There is something, a circle, and after you drown this circle into the bottle, which contains the water with soap, then you have this surface here, and when you blow in it on this surface, then soap bubbles are being produced by this stuff. So if you have this kind of thing, but with one of the sides which can be moved, then this is the conditions of this experiment. So when you move this, the force you need to apply is proportional to the length for example, of this wire here, and the proportionality coefficient is called surface tension coefficient. So now what follows from here is that I can determine the free energy. So this is the force. Okay, since this is the force, let's let it be a small letter f, because my large capital letter F is reserved for Helmholtz free energy. And as you know, the change of Helmholtz free energy from my previous part of the lecture is equal to the minus work done by the system at the constant temperature. So that means, if I do work on the system, that means that my change of the free energy is equal to F times, so let's say here we have x coordinate, F times dx, and that would be sigma L times dx. So that would be sigma times the area change. So if I change the area of my surface, I need to do the work which equals to sigma times dA. So from here follows that the free energy of my surface, oh, sorry, let me try to make it more visible. So the change of free energy is minus work done by the system at the constant temperature. Minus work done by the system is plus work done on the system. So that is force F times the displacement dx. Since force F is equal to sigma L, that would give me sigma L times dx. And L dx is actually the change of the area here, so this is sigma times dA. So when I have some surface, when I expand this surface, I do the work sigma times dA on the system, from which it follows that the free energy associated with the surface equals to sigma times the area of this surface, if I start from the area 0. So this is the free energy of the surface. And since I have free energy given by the canonic equation, in the case of the surface, volume should be replaced by the area. So when I have surface instead of gas, then I have a two-dimensional system instead of three-dimensional system, and my state of the two-dimensional system is described by the area, not by the volume. And also, for the free energy, canonic variables in the case of the surface are the temperature and the area. And I can determine this coefficient, the surface tension coefficient, at any kind of temperature. So I can conduct this experiment at different temperatures and get free energy as a product of surface tension coefficient, which is the function of only the temperature, by the area of the surface. So what I now have, I have a complete description of thermodynamic properties of my system, because I have here the function of temperature and area, which means that this is the canonic equation of state. And once I have the canonic equation of state, I can determine, I can determine the thermic and caloric equations of state. So let's start. So let's write it. Let's start with the writing this differential for the free energy. So in case of gas, I had minus S dt minus P dV. But I don't have gas anymore, so I have a surface. So I need to replace this by minus S dt minus, okay, instead of pressure, I have surface tension, so I have plus sigma times dA. Okay, so for exactly from this expression, I can get sigma by differentiating it over the area, and that is actually sigma of t, which is quite obvious. So I haven't introduced anything by doing this derivative. But I can determine the entropy of my surface, which is more interesting. The entropy is minus dF over dt at a constant area. So that gives me minus d sigma over dt multiplied by area. So that's the entropy. And now, as I know the entropy and the free energy, I can determine the internal energy of the surface. So that would be from this equation, that F is U minus Ts. So that means that internal energy goes the other way, that this is F plus Ts. So now I do this and get sigma times A plus T times minus d sigma over dt times area. So that gives me sigma minus t times d sigma over dt times A. So that's the internal energy. You see that the internal energy of the surface is remarkably different from the free energy of the surface. And that means that, well, this internal energy should be used when you try to calculate, for example, what happens with your surface if you undergo a adiabatic process. So now I have determined thermic and caloric equations of state for the surface. I have started with the free energy and got all of the other stuff. Well, I also want to do the same stuff for radiation, but I have no time for this because we are out of time for the lecture and we need to go to the seminar. But I guess I will send all of the necessary stuff by an email. If you have any questions about the lecture material, please don't hesitate to ask them. But as far as I guess, the significant part of the lecture was not understood, and I have expected this. So try to understand that when you study a bit more about multivariable calculus, particularly the stuff about Jacobians, because that is quite an important part of this lecture, actually. So if you are able to do this, then it would quite simplify all of the further adventures into the field of thermodynamics. And I would say that by means of these 3 lectures, I have done constructing the whole building of thermodynamics. So on a general level, I have produced everything you should know in order to apply thermodynamics to any thermodynamic system. And what we are going to continue to do from the next lecture, we are going to apply that to particular systems. And one of those particular systems is liquid-gas phase transition. And another particular system is an idea of van der Waals gas, which allows you to see the inner workings, how the inner workings of this theory apply to a particular system. Okay, let's have a 5-minute break before we start problem solving to get your brain ready for application of knowledge. Have you tried doing zero-level problems for this seminar? Please raise your hands, those of you who have tried doing them. As I said, if you try to do zero-level problems, then the lecture would be a bit more simpler for you to perceive, and also would be the seminar. But now, if you feel like what's going on there, then part of that can be attributed, for example, to my skill, but another part of that is attributed to you, who have not prepared for the lecture. And there is a third part of that, which is related to the complexity of this material itself. Of course, thermodynamics is very complicated, I assure you of that, compared to mechanics, actually. So when compared to mechanics, thermodynamics is much less intuitive. So in mechanics, you quite understand that, like, if you push this somewhere, then it goes that way, but not goes the other way. If it moves along the surface, then it doesn't jump out of the sudden, so it just moves along the surface. But in case of thermodynamics, there is no such kind of an intuition which might help you. So you need to develop that by solving multiple problems. And if you look at this theory, which involves some heavily mathematical stuff as a multivariable calculus, then you see that's actually a really difficult subject. It is beautiful, but it's mathematically heavy. So you can get lots of conclusions out of almost nothing. So what I actually do here is I derive some kind of a relationship between stuff based only on the fact that there are few functions of state, and nothing more than that.